On December 19th, 2025, something invisible is waiting for us in space. Not a rock, not a comet in the traditional sense. Something that might have torn a hole in the very fabric that protects Earth from the galaxy beyond. Scientists call it 3-Eye Atlas, an interstellar visitor now departing our solar system. But instruments are detecting something they never expected. A cold spot in the solar wind, a spike in cosmic radiation, and a geometry that puts Earth directly in line with whatever this object has left behind. Is it possible we're about to sail through a corridor carved between worlds, exposing us to raw galactic chaos? Stay with us, because what we've discovered challenges everything we thought we knew about how visitors from other stars interact with our cosmic home. The alignment happens in days. If you're as captivated by these cosmic puzzles as we are, consider subscribing to follow along as December 19th approaches, and we learn what really happens when Earth crosses this invisible threshold. Let us know in the comments where you're watching from, and what you think awaits us in the wake of 3-Eye Atlas. Are we witnessing the discovery of entirely new space physics, or is there more to this story than instruments can measure? Now, settle in and dive into this cosmic mystery. Part 1. The December 19th Geometry and Cold Spot Puzzle. Something is happening in the solar wind, and nobody is quite sure what it means. December 19th, 2025. That's the date when Earth, our Sun, and an interstellar visitor designated 3-Eye Atlas form what astronomers call an unusual alignment. You might think alignments happen all the time in space. Planets line up, moons eclipse suns, comets swing past Earth on predictable trajectories. But this alignment is different because it involves something that doesn't belong here. 3-Eye Atlas arrived from another star system entirely, carrying with it the physics and chemistry of a place we've never been. And on December 19th, Earth will cross directly through the path this object has traced across our solar system. The alignment itself wouldn't normally raise alarms. Space is mostly empty after all, and 3-Eye Atlas is safely 270 million kilometers away from us. No collision risk, no gravitational chaos, nothing Hollywood would turn into a blockbuster. But here's where things get strange. Solar wind monitors have detected something they're calling a cold spot, a region where the stream of charged particles flowing from our sun is behaving oddly. The protons in this zone are cooler than they should be. They're less dense than the surrounding wind. It's as if something carved a channel through the solar wind and that channel hasn't healed. Imagine a boat cutting through fog on a lake. Normally the fog swirls back together seconds after the boat passes, but what if it didn't? What if the wake stayed open, a visible corridor through the mist that persisted for hours, days, even weeks? That's the image some scientists are wrestling with as they study the data coming from instruments scattered across Earth and throughout the inner solar system. The cold spot appears to align with the trajectory of 3-Eye Atlas. It stretches behind the object like a tail, but it's not a tail of gas or dust. It's a trail carved into the solar wind itself, a region where the normal flow of particles has been disrupted in ways that shouldn't be possible for a simple comet. Then there are the cosmic ray detectors. These instruments measure high-energy particles that constantly bombard Earth from the galaxy beyond. Normally, cosmic rays arrive from all directions pretty evenly, filtered and deflected by the sun's magnetic field and our own planet's magnetosphere. But in recent weeks, detectors have registered an unusual directional spike. The excess radiation correlates precisely with the celestial coordinates of 3-Eye Atlas. It's as if the object is broadcasting a beam of galactic radiation toward us, or more disturbingly, as if it has opened a door through which radiation from deep space can flow more freely. Mainstream science has not yet confirmed anything resembling a magnetic tunnel or a cosmic breach. The data is preliminary, the signals are subtle, and there are plenty of alternative explanations being debated in journals and conference calls. Solar wind naturally has temperature and density variations. Cosmic ray counts fluctuate for all kinds of reasons, from solar activity to seasonal effects in Earth's atmosphere. But what has scientists paying close attention is the coincidence. The cold spot lines up with the object's path. The radiation spike points directly at its location, and December 19th is when Earth enters that alignment most directly. Solar wind is supposed to behave predictably. It flows outward from the sun in all directions, a supersonic stream of charged particles carrying the sun's magnetic field into interplanetary space. Any deviation from the expected temperature and density profile is noteworthy, because it suggests something is interacting with that wind in unexpected ways. A cold spot means energy has been removed from the protons somehow, or that they've been diverted, or that something has altered the magnetic structure through which they flow. And if that something is 3I Atlas, then we have to ask what kind of physics allows a comet-sized object to reshape the solar wind on such a scale. The question this video will explore is terrifying in its simplicity. Could a visitor from another star create a corridor that lets galactic radiation into our solar system? Could Earth be about to step into that corridor on December 19th? The analogy of a boat through fog doesn't quite capture the stakes. It's more like this. Imagine living inside a protective bubble. That bubble filters out dangerous radiation from the galaxy beyond, keeping you safe. Now imagine something punches a hole in that bubble, and the hole doesn't close. You're not in immediate danger because the hole is small and you're still mostly protected. But you're about to walk directly past that hole, and for a brief time, the unfiltered chaos of the universe outside will have a clear shot at you. Scientists are watching the data very closely because even small anomalies can reveal entirely new physics. Space weather is not a settled science. We're still discovering how magnetic fields interact on vast scales, how cosmic rays navigate the heliosphere, how the solar wind responds to objects moving through it. 3I Atlas is giving us a chance to study something we've never studied before, an interstellar object passing through our system fast enough and large enough to potentially leave a mark. And if it has left a mark, if the cold spot and the radiation spike are real and connected, then we need to understand what that means before Earth crosses the line on December 19th. The tone of this investigation is scientific curiosity meeting unsettling possibility. We're not talking about alien technology or deliberate sabotage. We're talking about physics, about the possibility that interstellar objects interact with solar systems in ways we haven't predicted. The universe doesn't need to be malicious to be dangerous. It just needs to be strange, and stranger than we've accounted for in our models. So let's dig into what we actually know about 3I Atlas, what we've observed that doesn't fit the normal comet template, and why the December 19th alignment has become a focal point for both excitement and unease in the scientific community. Part 2. Confirmed observations that don't fit. The normal comet template. 3I Atlas is officially an interstellar object, and that designation alone makes it extraordinary. Only 3 objects in recorded history have been confirmed to arrive from beyond our solar system. The first was Oumuamua, a strange cigar-shaped visitor that sparked endless debate about its nature. The second was 2I/Borisov, a comet that looked and behaved more or less as comets should. And now we have 3I Atlas, which is acting enough like a comet to be classified as one, but with enough peculiarities to keep astronomers up at night wondering what they're really looking at. NASA and the European Space Agency have confirmed the basics. 3I Atlas is travelling on a hyperbolic trajectory, which means it's moving too fast to be bound by the Sun's gravity. It came from somewhere else, and it's going somewhere else. Its closest approach to the Sun already happened months ago, and now it's speeding away from us on a path that will eventually take it back into the interstellar void. It will pass no closer than 270 million kilometres to Earth, which is comfortably beyond the orbit of Mars. There is zero collision risk. This is not an impact scenario. But distance from Earth doesn't mean absence of influence, especially when we're talking about plasma physics and magnetic fields that can extend across vast regions of space. What makes 3I Atlas unusual starts with its coma. All comets develop a coma, a cloud of gas and dust that forms when solar heat causes the ices in the nucleus to sublimate. That's normal comet behaviour. But the chemical composition of 3I Atlas's coma is anything but normal. Spectroscopic analysis has revealed unusually high concentrations of methanol and hydrogen cyanide compared to typical solar system comets. These aren't exotic molecules. Both are common in space, but the proportions are off, skewed in ways that suggest this object formed under different conditions than the comets we're used to studying. Methanol and hydrogen cyanide abundances tell us something about the environment where a comet was born. Solar system comets formed in the cold outer reaches of our planetary disk, where water ice dominated and other volatiles froze out in predictable ratios. 3I Atlas appears to come from a place where the chemistry was different, where perhaps the parent star had a different spectral type, or where the protoplanetary disk had different abundances of carbon and nitrogen compounds. The coma is essentially a chemical fingerprint, and the fingerprint doesn't match our family. Then there's the polarization data. When sunlight scatters off dust particles in a comet's coma, it becomes polarized in ways that depend on the size, shape, and composition of those particles. Astronomers measure this polarization to infer properties of the dust. 3i Atlas has shown negative polarization values that are unusually strong compared to other comets. Negative polarization typically means the dust grains are larger, or have different optical properties than expected. The exact interpretation is still being debated, but what's clear is that the dust coming off this object doesn't behave like dust from our comets. The particles might be fluffier, or more porous, or coated with different materials. Whatever the cause, it's another data point suggesting that 3i Atlas is fundamentally not quite like anything we've studied up close before. Water outgassing has been confirmed, which is reassuring in a way because it means 3i Atlas does have water ice like a proper comet. But even the water measurements are puzzling. The outgassing rates fluctuate in patterns that don't entirely match the simple models astronomers use to predict how comets brighten and fade as they approach and recede from the Sun. There are periodic variations, sudden bursts of activity, and asymmetries in the coma that suggest complex surface features or internal structures releasing gas unevenly. These confirmed peculiarities, taken individually, might not be alarming. Comets are diverse. Every comet has quirks, but 3i Atlas stacks quirk upon quirk until the overall picture starts to feel less like a comet, with unusual properties, and more like something our comet classification system isn't quite equipped to handle. It's comet-like, yes, but it's pushing the boundaries of what that means. Anomalies don't automatically mean danger. Science thrives on anomalies. They're the clues that lead to new discoveries, the threads you pull to unravel mysteries. But anomalies do mean there's more to understand, and when an object is hurtling through your solar system at tens of kilometers per second, understanding it fully before it leaves becomes urgent. We have a limited window to study 3i Atlas before it fades from view forever, vanishing back into the interstellar night from which it came. Every observation, every spectrum, every image is a piece of a puzzle we may never get another chance to solve. So here's the question that bridges us to the next layer of strangeness. If the physical properties of 3i Atlas are this unusual, if its chemistry and dust and outgassing don't quite fit our templates, then what about the space around it? What about the plasma environment it's creating as it moves through the solar wind? What if these physical anomalies we're seeing in the coma and the dust are fingerprints of something far stranger happening in the invisible electromagnetic structures trailing behind this visitor? The cold spot and the radiation spike suddenly seem less like isolated mysteries and more like symptoms of physics we haven't fully grasped yet. Part 3. Acceleration and tail. Mysteries. Physics or something else. Comet tails are supposed to be straightforward. The Sun releases a constant wind of charged particles that push gas and dust away from a comet's nucleus, creating tails that always point away from the Sun regardless of the comet's direction of travel. It's one of the most elegant demonstrations of solar wind pressure you can observe, a cosmic windsock showing which way the solar breeze is blowing. But 3i Atlas has been displaying tail behaviour that doesn't fit neatly into this simple picture, and that's where things start to get genuinely weird. Multiple observers have reported what's called an anti-tail, which sounds like science fiction but is actually a recognised phenomenon. An anti-tail appears to point toward the Sun rather than away from it, seemingly defying the very mechanism that creates comet tails in the first place. The standard explanation is that anti-tails are optical illusions caused by viewing geometry. When Earth passes through or near the plane of a comet's orbit, we can see dust that the comet left behind earlier in its path, and that dust appears to form a tail pointing in the opposite direction. It's a perspective trick, not a real reversal of physics. But here's what makes 3i Atlas's anti-tail notable. It's been observed consistently over weeks, with a symmetry and persistence that seem unusual even for this kind of geometric effect. Some amateur astronomers tracking the object have noted that the anti-tail structure looks more organised, more stream-like, than the hazy diffuse appearance typical of orbital dust lanes. It could still be an illusion. Viewing geometry can produce surprising effects, but it's also possible that 3i Atlas is shedding material in patterns we don't usually see, perhaps because of the unusual rotation or surface activity we've already noted. Then there are the reports of multiple jets. Jets are common on comets. They're localised bursts of gas and dust erupting from active regions on the nucleus, often triggered when fresh ice is exposed to sunlight. But 3I Atlas appears to have an unusual number of jets firing in different directions, creating a complex coma structure that shifts over time. Some observers have documented what looks like at least 4 or 5 distinct jet features active simultaneously. That's not unheard of, but it's on the high end of complexity for a comet this size. It suggests the nucleus has multiple active regions, possibly caused by an irregular shape or heterogeneous composition, where different ices are exposed on different facets. This is where the speculation about acceleration comes in. Several online discussions and amateur observation networks have noted that 3I Atlas seems to be moving slightly faster than gravitational models predict. The object should be following a precise hyperbolic orbit determined by the Sun's gravity and the initial velocity it had when it entered the solar system. But if it's outgassing asymmetrically, if those multiple jets are firing in uneven patterns, then the comet is essentially a natural rocket engine. Gas escaping from one side pushes the nucleus in the opposite direction, creating what's called a non-gravitational acceleration. This happens with regular comets too. It's well documented. The catch is that the magnitude of the acceleration should be predictable, based on how much gas the comet is releasing and in which directions. Some observers are claiming that 3I Atlas's motion doesn't quite match what the outgassing models predict, that there's a discrepancy suggesting either more powerful jets than expected or jets firing in unexpected directions. NASA and JPL have not confirmed any exotic propulsion mechanism. The official trajectory data accounts for outgassing effects as best as current models allow, but the speculation persists because the data is difficult to pin down precisely when you're tracking an object hundreds of millions of kilometers away with only ground-based telescopes and a few space-based instruments. Think about it like trying to predict where a sailboat will end up based on watching it from shore. You know the wind direction, you know the currents, but if the sail is torn in a way you can't see clearly, or if the rudder is damaged, or if there are gusts you didn't account for, your prediction will be off. And when that happens, you start wondering what you're missing. Are the forces more complex than you thought? Is there another factor you haven't included? In the case of 3I Atlas, the factor might just be unusually vigorous or directional outgassing. But until the models match the observations perfectly, there's room for doubt. How could unusual jet patterns affect larger solar wind structures? This is where the speculation starts to connect with the cold spot mystery. When a comet releases gas, it's not just tossing neutral molecules into space. Those molecules quickly get ionized by solar ultraviolet light, turning into charged particles that interact with the solar wind. A comet's ionized coma creates a complex plasma environment, a region where the solar wind slows down, heats up, and gets deflected around the obstacle. It's like a rock in a stream, creating eddies and turbulence in the flow. Now scale that up. 3I Atlas is releasing gas at rates high enough to maintain a large coma. That coma is continuously being ionized and interacting with the solar wind. If the outgassing is variable, if there are strong jets pulsing on and off, then the plasma environment around the comet is also variable, shifting and restructuring as the outgassing patterns change. And if the comet is moving fast enough, which it is because it's on a hyperbolic escape trajectory, then it's leaving behind a trail of disturbed plasma, a wake in the solar wind that might not settle back to normal immediately. Could that wake act like a current in a river? Could Earth be sailing into it on December 19th? The analogy is imperfect because space plasma doesn't behave exactly like water, but the core idea has merit. If 3I Atlas has created a persistent disturbance in the solar wind, a corridor where the plasma is cooler or less dense or magnetically structured differently, then crossing that corridor could expose Earth to conditions we don't normally experience. And if that corridor also allows galactic cosmic rays to penetrate more easily, then the stakes of crossing it become more significant. We're not talking about instant catastrophe, but we are talking about a measurable increase in radiation exposure, a temporary weakening of the protective bubble that keeps us safe. The jury is still out. Scientists are modelling these effects as fast as they can, running simulations of comet plasma interactions, comparing predictions to observations, trying to figure out what's normal variance and what's genuinely anomalous. But the clock is ticking, and December 19th is when Earth will have the most direct line of sight through whatever trail 3I Atlas has left behind. Part 4. Cosmic Ray. Imprints and solar wind cold regions. The solar wind is not empty space. It's a river of plasma, a supersonic stream of electrons and protons flowing outward from the sun, at speeds around 400 kilometers per second. This wind carries with it the sun's magnetic field, stretching and twisting those field lines into a structure called the interplanetary magnetic field. That field fills the entire solar system, creating what we call the heliosphere, a protective bubble that shields us from the full intensity of galactic cosmic rays. Without the solar wind and its magnetic field, Earth would be bathed in far higher levels of radiation from the galaxy beyond. Solar wind is hot. The protons have temperatures measured in hundreds of thousands to millions of degrees, even though the wind itself is so thin that it wouldn't feel hot if you could somehow stick your hand into it. Temperature in a plasma is about the kinetic energy of the particles, and solar wind protons are moving fast and energetically. So when scientists detect a cold spot, a region where the protons are measurably cooler than their surroundings, it's worth paying attention. Cold plasma means those protons have lost energy somehow. Maybe they've done work pushing against something. Maybe they've transferred energy to another population of particles. Maybe the magnetic field structure in that region has altered their behaviour. Cold spots in the solar wind are not entirely unknown. There are natural variations in temperature and density as the wind flows past planets, interacts with comet tails, or responds to changes in solar activity. But a cold spot that persists over time and appears to follow the trajectory of an interstellar object is unusual enough to demand explanation. The speculation is that 3i Atlas has carved a trail through the solar wind, a channel where the plasma has been disturbed and has not yet returned to its normal state. This would require the object to be shedding material at rates high enough to create a significant obstacle to the wind, and to be moving fast enough that the disturbance stretches out behind it rather than dissipating locally. Think of it like the contrails left by high-altitude jets. The airplane disrupts the air, and under the right atmospheric conditions, that disruption leaves a visible trail that can persist for hours. The trail isn't the airplane itself. It's a lingering signature of the airplane's passage, a region where the atmosphere has been altered. Similarly, a cold spot in the solar wind could be a contrail in plasma, a lingering signature of 3i Atlas's passage through our solar system. And if Earth crosses through that contrail, we're essentially flying through disturbed air, or in this case, disturbed plasma. But the cold spot is only half the puzzle. The other half is the cosmic ray spike. Cosmic rays are high-energy particles, mostly protons, that travel through the galaxy at nearly the speed of light. They originate from supernova, pulsars, and other violent astrophysical events far beyond our solar system. When they reach the heliosphere, they encounter the solar wind and its magnetic field, which deflect and slow many of them down. Earth's own magnetic field provides an additional layer of protection, funneling cosmic rays toward the poles and creating the auroras when the particles collide with our atmosphere. Cosmic ray detectors on Earth measure these particles indirectly. When a high-energy cosmic ray hits the upper atmosphere, it creates a cascade of secondary particles, including neutrons that can reach the ground. Detectors count these neutrons as a proxy for cosmic ray intensity. Normally, the count rates are pretty steady, with slow variations tied to the solar cycle, and occasional spikes during geomagnetic storms. But in recent weeks, some detectors have reported an increase in counts coming from a specific direction in the sky, and that direction aligns with the position of 3i Atlas. A directional increase in cosmic rays is significant because it suggests a structured path through the magnetic field, a channel where cosmic rays can penetrate more easily than they do elsewhere. The heliosphere isn't uniform. The interplanetary magnetic field has a complex topology, with sectors and current sheets and regions where the field is stronger or weaker. If 3i Atlas has disrupted that topology, if it has created a magnetic corridor by dragging field lines or compressing plasma, then cosmic rays travelling along that corridor might have an easier path toward the inner solar system and ultimately toward Earth. This is speculative. No published paper has confirmed a magnetic tunnel carved by 3i Atlas. The cosmic ray increases are subtle, and there are alternative explanations ranging from detector noise to coincidental solar wind structures. But the possibility is tantalizing and terrifying in equal measure. Imagine the heliosphere as an invisible fence made of magnetic field lines. Charged particles approaching from the galaxy get deflected by that fence, bouncing off or sliding along the field lines away from Earth. Now imagine something punches a gap in the fence, a narrow corridor where the field is weaker or oriented differently. Particles approaching from that direction wouldn't bounce off, they'd come through. Earth's magnetic shielding is a separate layer of protection, but it's not perfect. The South Atlantic anomaly is a well-known region where Earth's magnetic field is weaker, allowing more radiation to reach lower altitudes. Spacecraft passing through the anomaly often experience glitches, and astronauts on the International Space Station receive higher radiation doses when they pass over it. If the heliosphere also has weak spots, regions where the solar wind's protective effect is compromised, then the combination of a heliospheric weak spot and Earth's own magnetic quirks could create windows of vulnerability. This leads to the big speculative question that frames the entire December 19th concern. If 3i Atlas has carved even a gentle corridor through the heliosphere, a magnetic tube or plasma channel that allows galactic radiation to penetrate more easily, and if Earth's orbit carries us through that corridor on December 19th, then for a period of hours or days we could be exposed to elevated cosmic ray levels. Not apocalyptic levels, not civilization-ending radiation, but measurably higher than normal, enough to be detectable, enough to be interesting scientifically, and enough to raise questions about what this means for future interstellar visitors and for our understanding of space weather. The stakes are not about immediate danger. The stakes are about understanding the rules of the cosmic environment we live in, about discovering whether interstellar objects can leave lasting marks on the heliosphere, and about preparing for a future where we might encounter more of these visitors and need to predict their effects accurately. December 19th is a test case, a natural experiment where Earth crosses a potentially disturbed region and we get to measure what happens. Scientists will be watching their instruments closely, ready to see if the cold spot and the cosmic ray spike translate into observable changes at Earth. And if they do, we'll have learned something profound about how solar systems interact with the galaxy beyond. Part 5. Emerging Theoretical Models, Magnetic Tubes, Corridors and Deep Space Exposure. Mainstream physics tells us that magnetic fields, charged particles and plasma interact in predictable but complex ways. Solar flares erupt along magnetic field lines. The solar wind drags the sun's magnetic field into space. Planetary magnetospheres trap particles in radiation belts. All of this is well understood, governed by equations that physicists have refined over decades of observation and theory. But understanding the basics doesn't mean we can predict every possible configuration, especially when something unusual like an interstellar object enters the picture. A cometary wake is normally not powerful enough to carve long-range structures into the heliosphere. Comets are small, their outgassing is modest compared to the scale of the solar wind, and any disturbances they create tend to be localized and temporary. The plasma flows around them, the magnetic field reconnects and heals, and within hours or days the wake dissipates. But 3i Atlas is unusual in several ways that might make its wake more persistent. It's moving fast, which means it's continuously encountering fresh solar wind rather than lingering in its own disturbed region. It's outgassing at rates high enough to create a substantial ionized coma, and it's an interstellar object, which means it might carry with it plasma or magnetic properties from its origin system that interact differently with our solar wind than familiar comets do. This brings us to the concept of flux tubes. In solar physics, a flux tube is a bundle of magnetic field lines that act as a coherent structure, sometimes trapping plasma and guiding it along specific paths. Flux tubes are common in the solar atmosphere, playing a key role in phenomena like coronal loops and solar prominences. They can persist for days or weeks because the magnetic field has enough strength and organization to maintain the structure against the disruptive forces trying to tear it apart. Could a comet's wake create something analogous? Could 3i Atlas have generated a flux tube or magnetic corridor that extends far behind it, channeling plasma and allowing cosmic rays to travel along its length? This is theoretical territory. No one has observed a comet creating a long-lasting flux tube through the heliosphere. But the physics isn't impossible. If the outgassing from 3i Atlas is strong enough and directional enough, it could drag magnetic field lines along with it, creating a tube-like structure. If the object is moving fast enough, it could stretch that tube over vast distances before it dissipates. And if the interplanetary magnetic field has the right orientation, it might reinforce the tube rather than disrupting it, allowing the structure to persist longer than it otherwise would. Magnetohydrodynamics is the branch of physics that deals with these interactions, and it's notoriously difficult. The equations are nonlinear, meaning small changes in initial conditions can lead to wildly different outcomes. Simulations require supercomputers and still often miss details because the range of scales involved, from individual particle motion to global field structures, is too vast to capture fully. So when scientists talk about magnetic tubes and corridors, they're not making confident predictions. They're exploring possibilities, sketching out scenarios that are physically plausible, even if they're not yet confirmed. The relevance to cosmic rays is this. Magnetic field lines act as highways for charged particles. A particle spiralling around a field line will tend to stay on that field line, following it wherever it leads. If a flux tube connects the outer heliosphere to the inner solar system, cosmic rays could ride that tube inward, bypassing much of the deflection and energy loss they'd normally experience. The tube would act like a shortcut, a fast lane through the sun's protective barriers. This is how solar energetic particles sometimes reach Earth so quickly after a solar flare. They follow field lines that happen to connect the flare site directly to our planet, arriving hours before particles that have to take a more meandering route. Observed anisotropies in cosmic rays, meaning directional variations in the flux, are already known to science. Cosmic rays don't arrive uniformly from all directions. There are subtle excesses and deficits depending on where you look in the sky, and these anisotropies are linked to the structure of the interplanetary magnetic field and the boundaries of the heliosphere. What's unusual about the reported spike associated with 3I Atlas is its correlation with a specific transient object. Anisotropies are usually tied to long-lived structures or to the galactic magnetic field, not to something passing through on a timescale of months. Scientists are cautious about these interpretations because correlation does not equal causation. Just because cosmic ray counts increased from a certain direction at the same time 3I Atlas was in that direction doesn't prove the object caused the increase. There could be a background source, a distant supernova remnant or pulsar, that happens to lie along the same line of sight. There could be solar wind structures unrelated to the comet that are funneling particles in that direction. The data needs careful analysis, cross-referencing with other instruments, and ideally independent confirmation before anyone can claim a real discovery. But that caution doesn't diminish the intrigue. If further analysis supports the connection, if the cold spot and the cosmic ray spike are indeed tied to 3I Atlas, then we'll have stumbled onto a new aspect of space weather, a phenomenon where interstellar objects can leave measurable imprints on the heliosphere, and that discovery would raise immediate questions. How common is this? Do all interstellar visitors create these effects, or only certain ones? Under certain conditions? What determines how long the effects last? And most urgently, what are the implications for Earth when we happen to cross through one of these disturbed regions? The bridge to the next act of this investigation is recognizing that these fringe but scientifically inspired models are part of a larger conversation about how much we still don't understand. Space is not empty. It's filled with invisible structures, magnetic and electric, that shape the behavior of everything from individual atoms to entire planetary magnetospheres. 3I Atlas is giving us a rare chance to probe those structures, to test our theories against an object that doesn't play by the rules we're used to. The December 19th alignment is the climax of that test, the moment when theory meets observation in the most direct way possible. Are we about to discover new physics, or are we misunderstanding what we see? Only time and data will tell. Part 6. Beyond Comets. Could 3I Atlas be something fundamentally different? The standard model of comets is elegant in its simplicity. Comets are dirty snowballs, icy bodies formed in the cold outer regions of planetary systems. When they venture close to a star, the heat causes their ices to sublimate, releasing gas and dust that create the characteristic coma and tails. They're leftover building blocks from planet formation, frozen time capsules that preserve the chemistry of their birth environment. For centuries, this model has worked beautifully to explain almost everything we observe about comets in our solar system. But 3I Atlas is testing the limits of that model, pushing against the boundaries of what we thought we understood. Context matters here. Before 3I Atlas, only 2 confirmed interstellar objects had passed through our solar system in recorded history. The first was Oumuamua, detected in 2017, and it remains one of the most controversial astronomical discoveries of the century. Oumuamua didn't look like a comet. It showed no visible coma, no dust tail, nothing that suggested active outgassing. Its shape was bizarre, estimated to be either cigar-shaped or pancake-flat depending on whose analysis you trusted. And most puzzling of all, It accelerated as it left the solar system in a way that couldn't be explained by gravity alone. Scientists proposed outgassing as the explanation, but the lack of a visible coma made that hypothesis uncomfortable for many researchers. Then came 2I/Borisov in 2019 and it was a relief. Borisov looked like a comet, acted like a comet, had a nice dusty coma and behaved according to predictions. The astronomical community could breathe easy again. Interstellar objects were just comets from other star systems. Nothing too weird, nothing that challenged fundamental physics. But now we have 3I Atlas, and it's occupying an uncomfortable middle ground between Oumuamua's strangeness and Borisov's normalcy. It's definitely outgassing, definitely has a coma, definitely fits the comet category better than Oumuamua did. But it's doing all of that in ways that feel slightly off, like a familiar song played in the wrong key. Community consensus currently classifies 3I Atlas as comet-like, and most scientists are comfortable with that designation. But there are debates simmering beneath the surface. How comet-like does something have to be before we stop calling it a comet and start calling it something else? What if the definition of comet is too narrow, too shaped by the limited sample of objects we've studied from our own solar system? We've observed thousands of comets, but they're all siblings, all born from the same primordial material that formed the Sun and planets. 3I Atlas is a stranger from another family, and maybe our family's vocabulary doesn't quite capture what it is. Harvard astrophysicist Avi Loeb has been vocal about the possibility that some interstellar objects might not be natural at all. Loeb famously argued that Oumuamua could have been an artificial probe, a light sail or defunct piece of technology from an extraterrestrial civilization. The mainstream astronomical community largely rejected this hypothesis, favouring natural explanations even if those explanations required some hand-waving about unusual comet behaviour. But Loeb's willingness to consider unconventional possibilities has kept the conversation alive, forcing scientists to articulate exactly why they're confident in their natural explanations and where the uncertainties lie. For 3I Atlas, Loeb and others have pointed to what they call heartbeat patterns in the outgassing, periodic variations in brightness and activity that some interpret as too regular to be random. The idea is that if the outgassing pulses with a precise rhythm, maybe there's an internal structure controlling it, something more organised than the chaotic surface of a tumbling ice ball. Most scientists counter that rotation alone can create periodic patterns. As the nucleus spins, different faces with different ice concentrations point toward the Sun, creating natural variations in outgassing rates. No artificial mechanism needed. These controversial viewpoints are not mainstream, and it's important to be clear about that. The overwhelming majority of astronomers studying 3I Atlas believe it's a natural comet with unusual but explainable properties. But the fact that we're even having these conversations speaks to how much uncertainty still surrounds interstellar objects. We've detected exactly 3 of them. That's not a statistically significant sample. We can't confidently say what's typical and what's anomalous when our baseline is so limited. Every new interstellar visitor is a data point that could either confirm our expectations or overturn them entirely. The bigger question lurking behind these debates is whether we're missing key physics, not artificial technology necessarily, but natural processes that we haven't accounted for in our models because we've never had the opportunity to observe them before. Comets in our solar system formed under specific conditions, cooled over billions of years in the frigid darkness of the Oort cloud or Kuiper belt, and have been gently herded by the Sun's gravity ever since. Interstellar comets have wildly different histories. They might have been ejected violently from their home systems, experiencing gravitational slingshots that heated them or compressed them in ways our comets never experienced. They might have travelled through interstellar space for millions of years, bathed in galactic cosmic rays that altered their surface chemistry in profound ways. Think about it like comparing a river rock to a beach rock. They're both rocks, both shaped by erosion, but the specific forces that shape them leave different signatures. A river rock tumbles in flowing water, becoming smooth and rounded. A beach rock is battered by waves and rolled in sand, developing a different texture. If you only ever studied river rocks, you might be surprised by your first beach rock, wondering why it looks slightly wrong even though it's clearly still a rock. 3I Atlas might be our first beach rock, carrying the signatures of forces and environments we've never directly observed. This perspective shift matters because it changes how we interpret the anomalies. If we assume 3I Atlas should behave like solar system comets, then every deviation is puzzling and demands explanation. But if we accept that interstellar comets are their own category, shaped by different histories and environments, then the deviations become expected. The challenge is figuring out which deviations are meaningful and which are just natural variations within this new category we're still learning to understand. The cold spot and the cosmic ray spike could be one of those meaningful deviations, a sign that interstellar objects interact with the heliosphere in ways our native comets don't. Or they could be coincidences, unrelated phenomena that just happen to overlap in space and time. What if we're missing key physics not just in interstellar objects themselves, but in how they interact with solar systems they visit? That's the question driving the most intense scientific interest in 3I Atlas. This object is giving us a chance to study interstellar plasma dynamics, magnetic field interactions across stellar boundaries, and the transport of material and energy between star systems. These aren't just academic curiosities. Understanding these processes helps us model how planetary systems form, how they exchange material with the galaxy, and ultimately how common life-bearing worlds might be. If interstellar comets regularly carry organic molecules and water between star systems, they could be vectors for spreading the ingredients of life across the galaxy. But we can only explore those possibilities if we first understand what interstellar comets actually are and how they behave. So while the alien probe theories make headlines and fuel YouTube speculations, the real scientific frontier is much more subtle and potentially more profound. We're not looking for artificial structures or deliberate signals. We're looking for the fingerprints of interstellar space itself, the chemical and physical signatures that reveal what it's like out there in the vast darkness between stars. 3I Atlas is a messenger from that darkness, and the message it carries is still being decoded, one spectrum and one image at a time. Part 7. Galactic Ray. Processing surface chemistry as a recorded history. Cosmic rays are the galaxy's graffiti artists, leaving their marks on everything they touch. These high-energy particles, mostly protons travelling at a significant fraction of light speed, bombard every object floating in space. When they slam into solid surfaces, they trigger nuclear reactions, break molecular bonds, create new chemical species, and slowly erode the material over geological timescales. For small bodies like comets and asteroids that lack protective atmospheres or magnetic fields, cosmic ray exposure is a constant, relentless process that fundamentally alters their surface chemistry. And for an interstellar object like 3I Atlas, which has spent potentially millions of years travelling through the deep, galactic environment, that exposure could have created a surface unlike anything we've seen before. Scientists studying 3I Atlas have detected enhanced emissions of several organic molecules, particularly methanol and hydrogen cyanide. These molecules aren't unusual in themselves. Many solar system comets contain them, but the proportions are striking. 3I Atlas appears to have methanol abundances several times higher than typical comets, and its hydrogen cyanide signature is similarly elevated. These aren't small variations. They're large enough to suggest fundamentally different formation chemistry, or significant post-formation processing. Methanol and hydrogen cyanide are both carbon-bearing molecules that form in cold environments, where carbon monoxide ice reacts with hydrogen atoms. The specific ratios depend on temperature, pressure, radiation exposure, and the availability of different elements during formation. In our solar system, these ratios reflect the conditions in the outer protoplanetary disk 4.6 billion years ago. But 3I Atlas didn't form in our disk. It formed somewhere else, under different conditions, possibly around a star with different metallicity, or in a molecular cloud with different chemistry. The elevated organics could simply be a snapshot of those different birth conditions. But there's another possibility, one that ties directly into the cosmic ray story. When cosmic rays hit ice containing simple molecules like water, carbon dioxide, and carbon monoxide, they provide energy for chemical reactions that wouldn't happen otherwise. These reactions can produce more complex organics, including methanol and hydrogen cyanide. It's essentially radiation chemistry using particle bombardment instead of heat or light to drive molecular synthesis. Laboratory experiments have confirmed that irradiating comet like ices with protons similar to cosmic rays produces exactly these kinds of enhanced organic signatures. If 3I Atlas spent millions of years in interstellar space, it was bathed in galactic cosmic rays the entire time. Without the sun's protective heliosphere, without any planetary system's magnetic fields to deflect incoming radiation, the object would have been fully exposed to the unfiltered cosmic ray flux. Its surface layers would have been continuously processed, accumulating radiation damage and new chemical species. By the time it entered our solar system, its surface might have been fundamentally transformed compared to its original composition. This makes 3I Atlas potentially a recorder of ancient galactic environments. The chemical signatures we're detecting aren't just telling us about the object's birth, they're telling us about its journey, about the radiation environment it travelled through, about the processes that acted on it over cosmic timescales. It's like reading tree rings, except instead of recording seasonal variations in rainfall, the comet's surface chemistry records variations in galactic cosmic ray flux, exposure to supernova shock waves, passages through molecular clouds, and other events encountered during its interstellar voyage. The implications are fascinating. If we could fully decode the surface chemistry of 3I Atlas, we might be able to reconstruct parts of its history. How long has it been in interstellar space? Did it pass near any bright stars or supernova remnants that would have increased its radiation dose? Did it traverse dense molecular clouds where additional material might have accreted onto its surface? Each of these scenarios would leave distinct chemical fingerprints, and teasing them apart is one of the goals driving the intense observational campaign currently studying the object. But this discussion of cosmic ray processing also loops back to our central concern. If 3I Atlas has been heavily processed by cosmic rays, if its surface has been transformed by millions of years of bombardment, then what happens when that surface starts outgassing in the inner solar system? The molecules being released aren't pristine samples of the object's original composition. They're products of radiation chemistry, molecules that wouldn't exist in those abundances without cosmic ray exposure. And when those molecules ionize in sunlight and interact with the solar wind, are they creating plasma structures that behave differently than the plasma from normal solar system comets? This is speculative chemistry meeting speculative plasma physics, a double layer of unknowns that makes confident predictions impossible. But it raises the stakes of the December 19th alignment in an interesting way. We're not just passing through the wake of an unusual comet. We might be passing through the wake of an object whose very composition has been shaped by the deep space environment, an object that's releasing plasma with properties we've never encountered before. If that plasma has unusual magnetic properties, or if it interacts with the solar wind in unexpected ways, then the cold spot and cosmic ray spike might be direct consequences of 3I Atlas's unique surface chemistry. Think of it as the comet importing a piece of interstellar space into our solar system. The outgassing isn't just gas and dust. It's a sample of material that has been marinating in galactic radiation for eons, and when that material vaporizes and spreads through the heliosphere, it brings with it chemical and physical properties that reflect its origin. It's like adding a foreign ingredient to a familiar recipe. The basic processes, sublimation and ionization and plasma interaction, are all normal. But the end result might taste different because the starting material was fundamentally unlike what we're used to working with. The scientific community is still gathering data, still running analyses, still debating what these enhanced organic signatures really mean. But one thing is becoming clear. 3I Atlas is not just passing through. It's leaving a chemical and possibly magnetic signature behind. A trail that encodes information about both the object itself and the environment it travelled through to reach us. And on December 19th, Earth gets to sample that trail directly, experiencing for a brief moment what it's like to be immersed in the wake of an interstellar traveller. Whether that experience will be detectable at all, let alone significant, remains the open question that has scientists watching their instruments with a mixture of excitement and trepidation. Part 8. Hidden Anomalies. Anti-tails, persistent jets, and rotational oddities. Anti-tails are one of those phenomena that sound impossible until you understand the geometry. Normal comet tails point away from the sun, pushed by solar radiation pressure and the solar wind. An anti-tail appears to point toward the sun, seemingly violating basic physics. But it's not actually pointing toward the sun, it's a line of sight effect. When Earth passes through or near the plane of a comet's orbit, we're looking edge-on at a sheet of dust particles the comet shed earlier in its path. Those particles are still orbiting the sun on trajectories similar to the comet's, but because we're seeing them from a specific angle, they appear to form a line extending in the opposite direction from the main tail. It's a geometric illusion, like how a flat disk can look like a line when viewed edge-on. 3i Atlas has displayed an anti-tail structure that multiple observers have documented over a period of weeks. On the surface, this isn't alarming. Anti-tails happen. They're a known phenomenon observed on other comets. But what's caught attention is the persistence and symmetry of this particular anti-tail. Normally, anti-tail structures are ephemeral, visible for a few days as Earth's viewing geometry changes and then fading as we move out of the orbital plane. 3i Atlas's anti-tail seems to linger, maintaining a consistent appearance longer than simple geometric models predict. Some amateur astronomers tracking the object have noted that the anti-tail looks unusually stream-like, more organised and less diffuse than typical dust lane projections. It's almost as if there's a coherent structure there, a channel or filament of material rather than a scattered collection of particles. This could still be explained naturally. If the comet is shedding dust in a particularly directional way, if its jets are ejecting material preferentially in one direction, then the resulting dust distribution might have more structure than we typically see. But it's adding to the overall sense that 3i Atlas doesn't quite behave like a textbook comet. Then, there are the multiple jets. Jets are localized outgassing events where gas and dust erupt from active regions on a comet's nucleus. They happen when sunlight hits a patch of fresh ice, causing rapid sublimation that punches through any overlying dust layers. Most comets have a few active regions, maybe 2 or 3 jets visible at any given time. But observations of 3i Atlas have identified at least 4 or 5 distinct jet features active simultaneously, creating a complex asymmetric coma that changes appearance as the nucleus rotates. This level of activity suggests either an unusually irregular nucleus shape or a surface with highly variable composition. Imagine a potato-shaped object with patches of water ice, carbon dioxide ice, methanol ice, and various other frozen volatiles scattered across its surface. As it rotates, different patches face the sun, each sublimating at different rates depending on its composition and temperature. The result would be multiple jets firing in different directions, creating a coma that looks chaotic and dynamic rather than smooth and symmetric. Brightness variations add another layer of complexity. Several monitoring programs have reported what they're calling a heartbeat effect, periodic changes in the comet's brightness that repeat over hours or days. These variations are consistent with rotation, different parts of the nucleus reflecting more or less sunlight as they rotate into and out of view. But some observers claim the pattern is too regular, too predictable to be simple rotation of an irregular body. They see a clock-like precision that suggests either a very specific nucleus shape or some internal process controlling the outgassing in a rhythmic way. Professional astronomers are more cautious. Rotation plus uneven surface activity can create remarkably regular brightness patterns without invoking anything exotic. A nucleus with a prominent active region that faces the sun once per rotation period will brighten predictably every time that region comes around. Add a second active region on the opposite side, and you get 2 pulses per rotation. The math works out naturally, no mystery required. But getting the exact nucleus shape and activity distribution nailed down requires detailed observations that are challenging when the object is hundreds of millions of kilometers away. What's undeniable is that 3i Atlas is proving to be a goldmine for students of comet physics. Every image reveals new details. Every spectroscopic observation adds to the chemical inventory. Every brightness measurement refines our understanding of rotation and activity cycles. For scientists who spend their careers studying these icy visitors, 3i Atlas is the most interesting interstellar object yet, far more active and observable than Oumuamua ever was, and with more peculiarities than Borisov showed. But peculiar doesn't mean dangerous, and this is where public communication becomes tricky. Online communities love mysteries. They love anomalies. They love the idea that scientists are baffled or that there's something being hidden. And when you have an interstellar visitor displaying anti-tails, multiple jets, brightness oscillations, and unusual chemistry all at once, it's catnip for speculation. The challenge is distinguishing between what's genuinely puzzling to scientists and what's just normal comet behaviour that looks weird to untrained observers. Professional data on many of these features is still preliminary. Telescopes are booked months in advance, and getting observing time on the best instruments requires submitting proposals and waiting for approval. By the time observations are scheduled, reduced, analysed and published, the comet will be long gone. So much of what we know comes from rapid response observations, quick looks, and preliminary analyses shared via astronomers' telegrams and preprint servers. These early reports are invaluable for coordinating follow-up observations, but they're not the final word. Peer review and detailed analysis will come later, probably after the December 19th alignment has passed, leaving scientists to look back at the data and reconstruct what actually happened. In the meantime, the anti-tail, jets, and brightness variations feed into the larger narrative of 3I Atlas as an object that defies easy categorization. It's comet-like enough to be called a comet, but strange enough to keep everyone guessing about what's really going on. And that strangeness extends beyond the object itself to the space around it, to the plasma wake and the potential magnetic structures trailing behind. The visible oddities, the jets and tails we can photograph, might be symptoms of invisible oddities happening at the electromagnetic level. Disturbances in fields and plasmas that we can only detect indirectly through their effects on solar wind and cosmic rays. This is why December 19th matters. It's not just about crossing the comet's orbit. It's about crossing through the entire complex of disturbances the comet has created, visible and invisible, chemical and electromagnetic. Earth is sailing into unknown waters, and the anti-tail hanging there like a spectral signpost points the way. We'll find out soon enough whether there's anything waiting for us in that wake, or whether the whole thing will pass unnoticed except by the scientists and enthusiasts tracking every detail. Either way, 3I Atlas has already earned its place in the history books as one of the most fascinating visitors our solar system has ever received. Part 9, Heliospheric Structure and Weak Spots, Solar System in a Dynamic Plasma Sea. The heliosphere is our cosmic home, but most people don't even know it exists. It's the bubble of space dominated by the sun's influence, a region where the solar wind and solar magnetic field hold sway against the pressure of the interstellar medium beyond. The heliosphere extends far beyond the planets, reaching about 100 astronomical units from the sun before it finally encounters the heliopause, the boundary where solar wind pressure balances interstellar pressure and the sun's domain ends. We live inside this bubble, protected by it, shaped by it, and usually blissfully unaware of the complex plasma physics keeping us safe. The solar wind that creates the heliosphere isn't uniform. It varies with solar activity, speeding up and slowing down as the sun goes through its 11-year cycle of sunspot and flare activity. During solar maximum, when the sun is most active, the wind can gust to supersonic speeds, carrying intense magnetic fields and triggering geomagnetic storms when it slams into Earth's magnetosphere. During solar minimum, when the sun is quiet, the wind becomes steadier, but also allows more galactic cosmic rays to penetrate the inner solar system, because the magnetic fields aren't as tangled and disruptive to incoming particles. Right now, we're in the rising phase of solar cycle 25. The sun is becoming more active, but it hasn't reached maximum yet. This timing is relevant because it means the heliosphere is in a transitional state, neither fully shielding nor fully permeable to cosmic rays. It's a window of vulnerability, a time when the protective bubble is reconfiguring itself and temporary weak spots can appear. One of the most important structures in the heliosphere is the heliospheric current sheet. This is a vast undulating surface where the sun's magnetic field reverses polarity, north becoming south and south becoming north. Charged particles trying to cross, this sheet encounter complex magnetic turbulence that scatters and slows them. The current sheet isn't flat. It's warped into a wavy pattern that scientists sometimes call the ballerina skirt, because of how it ripples outward from the sun. As the sun rotates, Earth moves in and out of different sectors separated by the current sheet, experiencing different magnetic field orientations and different levels of cosmic ray exposure. Magnetic reconnection is another key process. This happens when oppositely directed magnetic field lines come together, break, and reconnect in new configurations, releasing enormous amounts of energy in the process. Reconnection drives solar flares, coronal mass ejections, and auroras. It's a fundamental mechanism by which magnetic energy converts to particle energy in plasmas, and it happens continuously throughout the heliosphere at various scales, creating a dynamic environment where nothing stays static for long. Understanding these structures helps contextualize any cold spot observations. Solar wind temperature and density naturally fluctuate as the wind flows past planets, through comet tails, and through regions of enhanced magnetic field. Declaring something a genuine anomaly requires proving it's outside the range of normal variation, And that's harder than it sounds when normal variation is itself poorly mapped. Scientists have solar wind monitors at a handful of locations: Earth, Mars, a few spacecraft scattered through the inner solar system. That's like trying to map Earth's weather with 5 thermometers. You can catch major patterns, but you'll miss a lot of details. The South Atlantic anomaly is a perfect example of how complex and quirky magnetic structures can be. This region over South America and the southern Atlantic Ocean is where Earth's magnetic field dips closer to the surface than anywhere else, creating a zone of enhanced radiation exposure. Satellites passing through the anomaly often switch to safe mode to protect their electronics. The International Space Station's astronauts receive measurably higher radiation doses when they fly through it, and the anomaly is moving and changing shape over time, drifting westward and potentially splitting into 2 separate regions as Earth's magnetic field evolves. If Earth's own magnetic field can have persistent weak spots, why not the heliosphere? The analogy isn't perfect because the heliosphere is shaped by flowing plasma rather than a solid planet's internal dynamo, but the principle holds. Complex magnetic structures develop localized quirks, regions where the field is stronger or weaker, more tangled or more ordered, and these quirks can have real consequences for radiation exposure and space weather. Any disturbance created by 3I Atlas would be superimposed on this already dynamic background. The cold spot, if real, isn't carving through pristine, uniform solar wind. It's carving through a medium that's already structured, already variable, already full of its own features and flows. Disentangling the comet's influence from natural heliospheric variability is the challenge scientists face. They need to compare measurements taken in the region where 3I Atlas passed with measurements from similar regions elsewhere in the heliosphere, looking for differences that can't be explained by normal variation. This is where space weather forecasting becomes both critical and frustrating. We can predict solar flares and coronal mass ejections reasonably well based on sunspot activity. We can model how those eruptions propagate through the solar wind. But predicting the fine-scale structure of the heliosphere, the exact temperature and density and magnetic field at any given location days in advance, remains beyond our capabilities. Too much turbulence, too much complexity, too few measurements. So when Earth approaches a potentially disturbed region on December 19th, scientists can watch it happen but can't confidently predict what they'll see until the moment arrives. The dynamic nature of the heliosphere also means that any structures created by 3I Atlas won't be static. The solar wind is flowing at hundreds of kilometers per second, sweeping disturbances along with it, stretching them out, mixing them with surrounding plasma. A cold spot created weeks ago when the comet was more active might have dissipated by now, or it might have evolved into something different, a trail of temperature variations rather than a coherent channel. The only way to know is to measure it directly, and December 19th gives us that opportunity. Placing this all in context, Earth isn't a fragile marble waiting to be shattered by cosmic forces. We've survived billions of years of solar storms, comet encounters, asteroid impacts, and galactic cosmic ray exposure. Our magnetosphere is robust. Our atmosphere is thick. Life found ways to thrive despite radiation levels that must have been far higher in the early solar system before the sun settled into its current stable state. But we're also increasingly dependent on technologies that are sensitive to space weather. Satellites, power grids, GPS systems, communication networks. All of these can be disrupted by geomagnetic storms and enhanced radiation. Understanding the heliosphere's structure and variability isn't just academic curiosity. It's practical necessity for a civilization that's extended its reach into space. So yes, the heliosphere has weak spots, transient and localized regions where protection is compromised, but those weak spots are manageable, observable, and most importantly, temporary. The question for December 19th is whether 3I Atlas has created a new weak spot, one we haven't encountered before, and whether passing through it will teach us something new about how our cosmic environment works. The answer might be mundane, it might be fascinating, but either way, we're about to sail through potentially disturbed waters, and the instruments will be watching. Part 10, Conspiracy versus Reality. What's legitimate debate versus noise? Science thrives on debate. Two scientists can look at the same data and reach different conclusions, not because one is wrong or dishonest, but because interpreting complex observations requires making assumptions, and those assumptions can differ. This is healthy. This is how science advances. Hypotheses clash, evidence accumulates, and eventually consensus emerges around the explanation that best fits all the data. But somewhere in the gap between preliminary observations and final consensus, speculation breeds, and not all speculation is equally grounded in reality. The distinction between peer-reviewed data and speculative theory matters enormously. Peer review is the process by which scientific papers are evaluated by independent experts before publication. It's not perfect. It doesn't catch every error, and it can sometimes be conservative to a fault, rejecting novel ideas that later prove correct. But it's the best quality control mechanism we have. When a paper passes peer review and gets published in a reputable journal, it means multiple scientists have examined the methods, checked the math, and agreed that the conclusions follow logically from the evidence presented. Speculative theory, by contrast, skips that vetting process. Its ideas shared on blogs, in YouTube videos, on social media, or in preprint servers before peer review. Some speculative theories are serious scientific proposals awaiting formal publication. Others are wild guesses dressed up in technical language to sound credible. And the average person trying to make sense of what's happening with 3i Atlas often can't tell the difference. They see scientific-sounding claims about magnetic tunnels and cosmic breaches, and assume these have the same evidentiary weight as NASA press releases, when in reality they might be based on nothing more than misinterpreted data or wishful thinking. Social media amplifies anomalies without context. A grainy image showing what looks like a second tail becomes proof of exotic physics. A brightness variation becomes evidence of artificial structures. A cosmic ray spike that's within normal variation gets reported as unprecedented. The algorithms reward engagement, and nothing drives engagement like mystery and alarm. So even legitimate scientific observations get distorted as they spread through online communities, each retelling adding layers of speculation until the original facts are buried under a mountain of interpretation. Let's be clear about what's actually been observed versus what's been speculated. NASA and ESA have confirmed that 3i Atlas is an interstellar comet with unusual chemical composition and outgassing patterns. That's fact. Multiple observatories have detected enhanced methanol and hydrogen cyanide emissions. That's fact. The object has displayed complex tail structures including what appears to be an antitail. That's fact. But the claims about persistent magnetic tunnels, about organised outgassing heartbeats implying artificial structures, about imminent cosmic radiation exposure on December 19th, those are speculations built on incomplete data and contested interpretations. The cold spot in the solar wind, for instance, hasn't been definitively confirmed by multiple independent measurements. Some instruments have registered temperature and density variations in the region where 3i Atlas passed, but others haven't seen anything unusual. This could mean the cold spot is real but localized, visible only from certain vantage points. Or it could mean it's an artifact of instrument calibration or data processing. Scientists are working to sort this out, comparing data sets, cross-referencing timestamps, trying to build a coherent picture from fragmentary evidence. The cosmic ray spike is similarly ambiguous. Yes, some detectors have reported increased counts from the direction of 3i Atlas, but cosmic ray background varies naturally, and picking out a real signal from statistical noise requires careful analysis. You need to account for atmospheric conditions, detector efficiency changes, and the possibility of localized sources unrelated to the comet. Preliminary reports suggest something interesting might be happening, but interesting isn't the same as confirmed. Why are people drawn to narratives of hidden truths and cosmic threats? Part of it is psychological. Humans crave patterns and explanations, especially for phenomena we don't fully understand. A mysterious interstellar visitor taps into primal anxieties about the unknown, about threats from beyond our control. Add in some legitimate scientific uncertainty, and it's easy to construct narratives where authorities are downplaying dangers or hiding evidence. These narratives are satisfying because they make the narrator feel informed and skeptical, rather than ignorant and helpless. But there's also genuine scientific fascination at play. 3i Atlas is objectively interesting. It's raising real questions that scientists are actively researching. The line between legitimate curiosity and unfounded speculation is blurrier than anyone wants to admit. A scientist wondering aloud whether the object might have created a persistent wake isn't making the same claim as a YouTuber declaring that Earth is about to be bathed in lethal radiation. But both statements can sound similar to someone without the expertise to parse the nuance. Here's a framework for distinguishing legitimate debate from noise. Ask where the claim originates. Is it from a published paper, a NASA press release, a university's official communication, or is it from anonymous forums, speculative blogs, channels known for sensationalism? Ask what evidence supports the claim. Are there multiple independent observations, or is it based on a single ambiguous data point? Ask what the scientific community's consensus is. Are most experts taking the claim seriously, or is it fringe speculation by one or two people? Applying this framework to 3I Atlas, we find that most of the dramatic claims don't hold up. Magnetic tunnels are theoretically possible, but not confirmed by any peer-reviewed publication. The December 19th alignment is real, but there's no consensus that it poses any measurable risk. The anomalous chemistry and tail structures are genuinely interesting to scientists, but interesting means worth studying, not proof of anything exotic. What verified data confirms is this. 3I Atlas is an interstellar comet displaying unusual but not unprecedented behaviour. It's being studied intensively by observatories worldwide. Its closest approach to Earth will be safely distant. Any effects from its passage through the solar system are likely to be subtle and detectable only by sensitive instruments. Scientists are excited about the opportunity to study it, but excitement stems from scientific curiosity, not alarm about imminent danger. Mystery doesn't equal threat. This is perhaps the most important takeaway. The universe is full of phenomena we don't fully understand, and that's wonderful. It means there's still science to do, discoveries to make, frontiers to explore. 3I Atlas is mysterious in the best sense of the word. It's challenging our assumptions, forcing us to refine our models, giving us data that will take years to fully analyse and understand. But a mystery is just an unanswered question. It's not evidence of conspiracy or danger or cosmic catastrophe. The transition to our final act involves recognising that while 3I Atlas is fascinating, it's just one example of a much larger cosmic story. The universe is stranger and more dynamic than most people realise. Every year brings new discoveries that reshape our understanding. Some of those discoveries involve objects like 3I Atlas. Others involve entirely different phenomena, particle physics mysteries, extreme astrophysical events, strange behaviours of space itself. If we're going to have an honest conversation about cosmic mysteries and potential dangers, we need to broaden the view beyond a single comet and look at the wider context of what's happening in space science right now. That's where we're headed next. Part 11. New 3I Atlas. Images and tracking drills. The latest images from Hubble Space Telescope arrived just days ago, and they're spectacular in what they reveal. These aren't fuzzy dots or smeared streaks. They're detailed portraits of 3I Atlas's coma, showing the intricate structure of gas and dust surrounding the nucleus. You can see the multiple jets we've been discussing, resolved as distinct features radiating outward from the central condensation. You can see how the coma is asymmetric, brighter on one side than the other, evidence of the directional outgassing that makes this object so interesting. And you can see the tails, plural, extending in different directions as solar radiation pressure and solar wind momentum separate dust from gas. The European Space Agency has contributed observations from its ground-based telescopes and from spacecraft positioned throughout the inner solar system. ESA's Solar and Heliospheric Observatory, known as SOHO, has been tracking 3I Atlas as it moves through the field of view. SOHO was designed to study the Sun, but it's also discovered thousands of comets over its decades of operation, catching them as they swing close to our star. 3I Atlas won't get that close, but SOHO's coronagraphs can still detect it against the backdrop of space, providing data on how the comet's coma evolves in response to changing solar wind conditions. These images aren't just pretty pictures, they're scientific gold. Every pixel contains information about the comet's composition, activity level, and interaction with its environment. By comparing images taken days or weeks apart, scientists can measure rotation rates, track how jets turn on and off, and watch how the coma expands and changes shape. It's like having a time-lapse video of a dynamic cosmic event, compressed from months into minutes. What these observations are also doing is providing a training ground for planetary defence. Now, 3I Atlas poses no threat. We've established that. But it's exactly the kind of object our planetary defence networks need to practice tracking. it's moving fast on a hyperbolic trajectory, similar to how a potentially hazardous asteroid on a collision course might behave. It's outgassing, which complicates trajectory predictions because the jets create non-gravitational forces, and it's at a challenging distance, far enough that precision measurements require careful coordination between multiple observatories. Organisations like NASA's Planetary Defence Coordination Office are using 3i Atlas as a live-fire exercise. How quickly can we detect objects like this? How accurately can we determine their orbits? What observing strategies work best for tracking fast-moving visitors? If a genuine threat appeared tomorrow, an asteroid or comet on a collision trajectory discovered with only months of warning, we'd need to characterise it rapidly and precisely. 3i Atlas is letting us test and refine those capabilities in a low-stakes environment, where the only consequence of error is missed scientific opportunity rather than planetary catastrophe. Software tools like NASA's Eyes on the Solar System have been updated to include 3i Atlas's trajectory. Anyone with an internet connection can now visualise where the object is relative to Earth, the Sun, and other planets. You can rewind time to see its approach, fast forward to watch it depart, adjust your viewing angle to understand the geometry of the December 19th, alignment. These visualizations make abstract orbital mechanics tangible, helping people grasp the three-dimensional dance happening in space. Mission scientists are racing against time because the window of opportunity is closing. As 3i Atlas recedes from the Sun, it's getting fainter. Its outgassing is slowing as it returns to the cold of deep space where ices no longer sublimate. Within months, it will be too dim for all but the largest telescopes to detect. Within a year or two, it will be effectively invisible, lost in the darkness between stars. Every observation scheduled now might be the last chance we ever get to study this particular visitor. Multiple spacecraft are contributing to the campaign. NASA's Stereo mission, which consists of 2 spacecraft orbiting the Sun, ahead of and behind Earth, provides different viewing angles that allow 3-dimensional reconstruction of the comet's structure. These stereoscopic observations are crucial for understanding whether features in the coma are real structures or projection effects. The upcoming Punch mission, designed to study the solar wind and corona, is being prepared with 3i Atlas in mind as a potential calibration target if the timing works out. What strikes anyone following this campaign is the level of international cooperation. Observatories in Chile, Hawaii, Spain, South Africa, and Australia are all contributing data. Amateur astronomers with backyard telescopes are reporting observations that complement professional surveys. Space agencies that sometimes compete for funding and prestige are pooling resources and sharing data freely because everyone recognizes the scientific value. 3i Atlas belongs to no single nation or organization. It's a gift from the galaxy to all of humanity, a chance to learn something new about the universe we inhabit. The images themselves have an aesthetic power beyond their scientific content. There's something humbling about seeing a visitor from another star system rendered in false colour. The coma glowing in shades of blue and green that represent different molecules, the tails streaming across the frame like cosmic banners. It's a reminder that we live in a dynamic universe, where objects travel between stars, where nothing is truly isolated, where the galaxy is connected by invisible highways of gravity and motion. These newest observations are also revealing details that weren't apparent in earlier data. The anti-tail structure appears to have evolved, becoming less prominent as the viewing geometry changed. Some of the jets have strengthened while others have faded, suggesting that the nucleus's rotation is bringing different surface regions into sunlight. The overall brightness has plateaued rather than continuing to fade as quickly as models predicted, hinting that there might be fresh ice being exposed from beneath an insulating dust layer. Every one of these details feeds into models that scientists are continuously refining. Comet physics is complex enough that no single model captures all the relevant processes. Researchers use different approaches, some emphasizing thermal models that track how heat penetrates the nucleus, others focusing on gas dynamics and how pressure builds up beneath the surface, still others concentrating on the dust behavior once it's been lifted off. Reconciling these different models into a coherent picture requires comparing their predictions to observations, and 3i Atlas is providing an unprecedented dataset for those comparisons. The hopeful tone here is deliberate. Yes, there are mysteries and anomalies. Yes, there are unanswered questions about cold spots and cosmic rays. But the overwhelming story of 3i Atlas is one of scientific opportunity seized, observatories pivoting to target an unexpected visitor, researchers setting aside other projects to focus on time-sensitive data collection. The global astronomical community coming together to make the most of a fleeting chance to study something extraordinary. This is exploration at its finest, driven not by fear but by curiosity, not by speculation but by the desire to know. As December 19th approaches, the instruments will be ready. The telescopes will be tracking. The cosmic ray detectors will be recording. Whatever happens, whether Earth crosses through a disturbed region or passes through undisturbed space, we'll have the data to analyse and learn from. And that data will shape our understanding not just of 3i Atlas, but of interstellar objects in general, preparing us for future visitors and deepening our knowledge of the galactic environment we're all travelling through. The comet isn't a threat, it's a teacher, and we're eager students. Part 12, Kaleidoscale Particles from Antarctica, a new frontier in high-energy astrophysics. Antarctica is the best laboratory on Earth for studying cosmic rays, and that's not because of any equipment we've placed there. It's because of the ice itself. The Antarctic ice sheet is kilometres thick, ancient and pristine, and it acts as a massive particle detector. When ultra-high-energy cosmic rays slam into the ice, they create cascades of secondary particles and radio frequency pulses that specialised antennas can detect. These pulses encode information about the original cosmic ray's energy and direction, allowing scientists to reconstruct events that would be impossible to observe any other way. Recent observations from Antarctica have revealed something unexpected. High-altitude balloon experiments flying over the continent detected radio pulses consistent with particles carrying energies that shouldn't exist, according to standard models. These aren't garden-variety cosmic rays. These are particles so energetic that they rival what we create in the most powerful particle accelerators on Earth, except they're occurring naturally in the atmosphere. The technical term is ultra-high-energy cosmic rays, and they've been known for decades, but the recent detections show patterns that don't match expectations. The standard story of cosmic rays goes like this. They're produced by violent astrophysical events, mostly supernova explosions and the shock waves those explosions drive through interstellar space. As charged particles get caught in these shocks, they bounce back and forth, gaining energy with each crossing until they reach tremendous speeds. Eventually they escape and travel through the galaxy as cosmic rays. The highest energy cosmic rays we detect probably come from outside our galaxy, from active galactic nuclei or other exotic sources. But there's a catch called the GZK cutoff. The GZK cutoff, named after physicists Grayson, Zatsepin and Kuzmin, predicts that cosmic rays above a certain energy should be extremely rare. This is because ultra-high energy protons interact with the cosmic microwave background radiation that fills the universe, producing pions and losing energy in the process. Any cosmic ray travelling more than about 100 million light-years should have its energy degraded below the GZK threshold. So when we detect cosmic rays above that threshold, they either originated relatively nearby in cosmic terms, or something about our understanding of particle physics is incomplete. The Antarctic detections are showing an excess of events that seem to be coming from specific directions in the sky, and those directions don't align neatly with known astrophysical sources. It's as if there are cosmic ray hotspots, regions where ultra-high energy particles are more common than they should be. Some physicists are wondering whether these could be signatures of new physics, interactions we haven't accounted for, or perhaps evidence of exotic particles like the hypothetical dark matter particles that supposedly make up most of the universe's mass. This connects thematically to the 3i Atlas story because both involve unexpected signals from space that challenge our models. Just as 3i Atlas might be leaving a trail through the heliosphere that alters cosmic ray propagation, these Antarctic detections suggest the cosmic ray environment is more structured and complex than we thought. Space isn't a uniform background of radiation. It's textured with hotspots and cool spots, channels and barriers, shaped by magnetic fields and plasma dynamics, on scales we're only beginning to map. Understanding cosmic rays at these extreme energies pushes the boundaries of particle physics. The energies involved are beyond anything we can replicate in our accelerators. The Large Hadron Collider, the most powerful accelerator ever built, smashes protons together at energies around 14 trillion electron volts. The cosmic rays being detected in Antarctica have energies exceeding 100 million trillion electron volts. That's nearly 10 million times more energetic. If we want to study particle physics at those scales, nature is our only laboratory. What these particles are doing to Earth's atmosphere is also fascinating. When they hit, they create extensive air showers, cascades of secondary particles that spread across kilometres of sky. These showers produce light, radio waves, and particle tracks that detectors can measure. By studying the shower's properties, scientists can infer the energy and type of the original cosmic ray. Was it a proton? An atomic nucleus? Something more exotic? The answer tells us about the source and about the physics governing particle interactions at energies we can't reach artificially. But here's where things get unsettling in a productive scientific way. If ultra-high energy cosmic rays are more common than models predict, if they're arriving from unexpected directions, then either our models of cosmic ray sources are wrong, or our models of how cosmic rays propagate through space are wrong, or both. The magnetic fields of the galaxy are supposed to scatter charged particles, randomizing their directions so that by the time they reach Earth, we shouldn't be able to trace them back to specific sources. Yet the Antarctic data suggests we can. One possibility is that the most energetic cosmic rays are relatively unaffected by magnetic fields because their momenta are so enormous. They travel nearly in straight lines despite the galaxy's magnetic web. Another possibility is that the magnetic field structure between the source and Earth has coherent features, channels or filaments that guide particles preferentially. This would be similar to the speculative magnetic tunnels we discussed in the context of 3I Atlas, except on galactic scales rather than heliospheric scales. Earth's magnetosphere responds to these high-energy particles in ways we're still discovering. Most cosmic rays get deflected by Earth's magnetic field, funneled toward the poles where they create auroras. But the highest energy cosmic rays punch through with barely any deflection, depositing their energy directly into the upper atmosphere. If cosmic ray flux increases, even modestly, the atmospheric effects could be measurable. More ionization, more secondary particles, potential impacts on chemistry and cloud formation. These aren't catastrophic effects, but they're scientifically interesting and potentially relevant to understanding past climate variations. This research exemplifies how unexpected discoveries drive science forward. Nobody predicted these Antarctic anomalies. They emerged from data collected for other purposes, noticed by sharp-eyed researchers who recognized that the patterns didn't match expectations. Now there's a rush to confirm the findings with independent detectors, to gather more statistics, to rule out instrumental artifacts and terrestrial interference. If the anomalies hold up, they'll force revisions to textbooks and spark new theories about cosmic ray sources and propagation. The parallel to 3I Atlas is clear. Both stories involve detecting unexpected signals from space, wrestling with incomplete data, debating interpretations, and recognizing that the universe is more complex than our current models capture. Both remind us that despite centuries of scientific progress, we're still discovering fundamental aspects of our cosmic environment. And both highlight how fragile our understanding can be, how a few anomalous measurements can unsettle established theories and open new lines of inquiry. What this means for future cosmic exploration is profound. As our detectors become more sensitive, as our networks become more global, as our analysis techniques become more sophisticated, we're going to discover more and more of these anomalies. Some will turn out to be instrumental artifacts or statistical flukes, but some will be real, pointing toward new physics that we haven't imagined yet. The Antarctic cosmic ray mystery is one example, the 3I Atlas enigma is another, and there are surely dozens more waiting to be uncovered in data that's already been collected, but not yet fully analysed, or in observations that haven't been made because we didn't know to look. Part 13, Record-Breaking Gamma Ray Burst in Extreme Physics. On October 9th, 2022, Earth was bathed in the light from the most powerful gamma-ray burst ever recorded. The event, designated GRB 221009A, released more energy in a few minutes than the Sun will emit over its entire 10 billion year lifetime. It was so bright that it ionized Earth's upper atmosphere, triggering lightning detectors and overwhelming X-ray satellites that weren't even pointed toward it. Astronomers immediately dubbed it the Boat, the brightest of all time, and nearly 3 years later, we're still uncovering implications from that single cosmic explosion. Gamma-ray bursts are the universe's most energetic electromagnetic events. They occur when massive stars collapse into black holes, or when neutron stars merge, creating jets of matter and radiation moving at 99.9% the speed of light. When one of these jets happens to point toward Earth, we see a brief flash of gamma rays followed by a fading afterglow across the electromagnetic spectrum. Most bursts last only seconds, but their power is incomprehensible. A typical gamma ray burst releases more energy than all the stars in the observable universe combined produce in the same time span. The boat originated from a galaxy roughly 2 billion light-years away, which in cosmic terms is relatively close. If it had occurred in our own galaxy, say within a few thousand light-years, the radiation would have been devastating. Earth's ozone layer would have been obliterated. Extinction-level ultraviolet radiation would have reached the surface. DNA would have been shredded in any organism exposed to open sky. Some paleontologists have speculated that past mass extinctions might have been triggered by nearby gamma-ray bursts, though evidence for this remains circumstantial. What makes the boat scientifically valuable beyond its record-breaking brightness is what it's teaching us about physics at extremes. The jets from gamma-ray bursts accelerate particles to energies comparable to what we're detecting in Antarctica. These jets are natural particle accelerators, laboratories where matter behaves in ways we can barely replicate. By studying the burst spectrum, its polarization, and its evolution over time, physicists can test theories of quantum electrodynamics, general relativity, and exotic matter states that exist only in such violent environments. One of the mysteries the boat deepened involves afterglow emission. Most gamma-ray bursts have afterglows that fade predictably, dimming over hours and days as the expanding jet collides with surrounding material and loses energy. But the boat's afterglow showed unusual variability, brightening and fading in ways that suggest complex structure in the jet or in the surrounding environment. Some models propose that we're seeing multiple shock fronts colliding, creating interference patterns in the emission. Others suggest we might be seeing effects from the black hole's magnetic field as it reorganizes after the collapse. Detection methods for gamma-ray bursts involve a global network of satellites. NASA's SWIFT satellite is designed to rapidly localize bursts, slewing its instruments toward the source within seconds. The Fermi Gamma Ray Space Telescope provides high-energy coverage, measuring photon energies up to hundreds of billions of electron volts. Ground-based optical and radio telescopes follow up, tracking the afterglow and searching for host galaxies. This coordinated approach has revolutionized the field, allowing detailed studies of events that are over almost as soon as they begin. The implications for high-energy astrophysics extend beyond gamma-ray bursts themselves. These events are cosmic laboratories where we can study processes that don't occur anywhere else. How do black holes form? What happens to matter at nuclear densities? How do magnetic fields behave when they're strong enough to warp space-time? Gamma-ray bursts provide observational anchors for theories that would otherwise remain purely mathematical. Every burst is a new experiment, nature performing physics that we could never replicate artificially. Connecting this to Earth's cosmic safety requires acknowledging an uncomfortable truth. We are safe from most cosmic catastrophes most of the time. The universe is vast, and dangerous events are rare and usually distant. But not all threats can be dismissed as infinitesimally unlikely. A gamma-ray burst from within our galaxy, particularly one pointing toward us, would be a genuine existential threat. The good news is that we haven't identified any star systems nearby that are likely to produce such a burst in the foreseeable future. The bad news is that foreseeable doesn't mean never, and on geological timescales, rare events become inevitable. Using this as a science fiction hook isn't about fear-mongering, it's about perspective. Earth exists in a universe that is simultaneously majestic and hazardous. Most of the time, we're protected by distance, by our atmosphere, by our magnetic field, by the simple fact that space is mostly empty. But that protection isn't absolute. Events like the boat remind us that the universe operates at energy scales that dwarf anything in human experience. A supernova in our stellar neighbourhood, a gamma-ray burst aimed our way, a rogue black hole passing through the solar system, these are all statistically unlikely but physically possible scenarios that could reshape or end life on Earth. Future observations will continue to push our understanding. New satellites with better sensitivity and faster response times are being designed. Ground-based observatories are being equipped with instruments that can capture the earliest moments of afterglow emission. Gravitational wave detectors are joining the effort, listening for the space-time ripples that neutron star mergers produce alongside their electromagnetic fireworks. Every new capability opens a window into cosmic violence, giving us better tools to predict and understand the most energetic events in the universe. The boat also illustrates the importance of continuous monitoring. It wasn't predicted, it just happened, and the only reason we caught it in such detail is that our satellite network was already in place, watching the sky constantly. If we want to understand the full spectrum of cosmic phenomena, from gentle comet passages to cataclysmic explosions, we need persistent observation. We need instruments that never blink, that record everything, that can respond instantly when something extraordinary occurs. The data from those instruments becomes the raw material for scientific discovery and for preparing humanity to navigate a cosmos that is beautiful, mysterious, and occasionally dangerous. Part 14. Space hurricanes and magnetospheric phenomena that reshape planetary environments. In August 2020, Chinese researchers announced the discovery of something that wasn't supposed to exist: a space hurricane. This wasn't a metaphor or an analogy. It was an actual rotating storm structure in Earth's upper ionosphere, spanning nearly 1,000 kilometers and persisting for 8 hours. The storm was made of plasma rather than air, and instead of rain it deposited electrons into the atmosphere. But its spiral structure, its eye and its dynamics were remarkably similar to terrestrial hurricanes, suggesting that some fluid patterns are universal, whether you're dealing with air, water or ionized gas. Space hurricanes form through a process called magnetic reconnection, the same mechanism that drives auroras and solar flares. When the solar wind carries magnetic fields that are oriented opposite to Earth's magnetic field, the fields can break and reconnect, releasing tremendous energy. This energy accelerates charged particles, which then spiral along field lines into the upper atmosphere. Under the right conditions, these spiraling particles can organize into a rotating structure with a calm central eye surrounded by a wall of energetic plasma. What makes this discovery significant is that it happened during a period of very low solar activity. Traditionally, scientists thought you needed strong solar wind disturbances to drive dramatic magnetospheric events, but the space hurricane occurred when the sun was quiet, suggesting that Earth's magnetosphere has its own internal dynamics that can create storms even without external forcing. It's like discovering that your house can generate its own wind patterns regardless of what's happening outside. The mechanisms driving space hurricanes involve complex feedback between different plasma populations. The ionosphere, the region of Earth's upper atmosphere where atoms are ionized by solar ultraviolet light, isn't passive. It can generate its own electric currents and electric fields that feed back on the magnetosphere above. When these fields interact with incoming solar wind structures, they can amplify disturbances, turning modest perturbations into full-blown storms. It's a system with positive feedback loops, where small changes can cascade into large effects. Why space hurricanes matter extends beyond academic curiosity. These storms affect radio communication, particularly at high latitudes where the ionosphere's structure is most variable. They can create sudden ionospheric disturbances that disrupt GPS signals and high-frequency communications used by aviation and maritime operations. They deposit energy into the atmosphere that can affect chemistry and potentially influence cloud formation. Understanding how and when these storms form is crucial for space weather forecasting and for protecting technological systems that depend on stable ionospheric conditions. The discovery also illustrates why phenomena on all scales, from comets to hurricanes, shape our cosmic experience. Earth's environment isn't neatly divided into isolated layers. The surface, atmosphere, ionosphere, and magnetosphere are coupled systems where events in one region affect the others. A solar storm can trigger auroras, which heat the upper atmosphere, which changes atmospheric circulation, which potentially influences weather patterns at lower altitudes. The connections are complex and not all fully understood, but they're real and measurable. Analogies to terrestrial weather are useful but imperfect. On Earth, hurricanes are driven by thermal gradients in the ocean and atmosphere. Warm water evaporates, rises, releases its heat when it condenses and drives circulation. Space hurricanes are driven by electromagnetic forces, magnetic reconnection, and plasma instabilities rather than thermodynamics. But the mathematics describing rotational fluid dynamics is similar, which is why the structures look alike. It's an example of convergent patterns emerging from different physical processes. Clarifying that space hurricanes are observed phenomena with real data backing them is important because it distinguishes them from the more speculative ideas we've discussed about 3i Atlas. Space hurricanes have been detected directly, imaged by satellites, and studied in detail. The physics explaining them is well established, even if some details remain mysterious. They're not fringe speculation. They're mainstream space physics, published in peer-reviewed journals and accepted by the scientific community as real features of Earth's magnetosphere. The connection to the broader theme of this investigation is recognizing how dynamic and interconnected space environments are. Earth doesn't float in isolation. We're immersed in the solar wind, coupled to the sun's magnetic field, constantly exchanging energy and particles with the space around us. When something like 3i Atlas passes through the solar system, it's not passing through empty vacuum. It's passing through a structured environment filled with flows and fields, and its passage can perturb those structures in ways that ripple outward, potentially reaching Earth. Space weather has become a recognized hazard that governments and industries take seriously. NOAA operates the Space Weather Prediction Center, issuing forecasts and warnings similar to terrestrial weather services. Power companies prepare for geomagnetic storms that can induce currents in transmission lines, potentially causing blackouts. Satellite operators plan maneuvers around predicted solar storms to avoid damaging their spacecraft. Airlines reroute polar flights when radiation levels spike. The economic and safety implications are significant enough that improving space weather forecasting is a priority for research funding. Future research will undoubtedly discover more types of magnetospheric phenomena we haven't seen yet. Space hurricanes were hiding in data that had been collected for years before anyone recognized the pattern and realized what they were looking at. How many other features are lurking in datasets waiting to be discovered? How many phenomena occur too rarely or too briefly to have been captured yet? As our instrumentation improves and our coverage becomes more comprehensive, we'll fill in these gaps, building a more complete picture of how planetary magnetospheres behave. The reflection this invites is humbling. Earth's magnetosphere, which we've been studying intensively for decades, still surprises us. We're still discovering basic phenomena like space hurricanes. If we're this ignorant about our own planet's immediate environment, how much more uncertain are we about the heliosphere, about cosmic ray propagation, about the effects of interstellar visitors? The proper response isn't fear, it's recognition that science is an ongoing process, that understanding deepens gradually through observation and analysis, and that being surprised by nature is a feature rather than a bug of the scientific enterprise. Space hurricanes and 3i Atlas and Antarctic cosmic ray anomalies are all part of the same story. They're reminders that the cosmos is active, that forces we can't see with our eyes are constantly shaping our environment, and that we've barely scratched the surface of understanding the full complexity of space. December the 19th might reveal another piece of that complexity if Earth crosses through a disturbed region left by 3i Atlas, or it might pass uneventfully, teaching us that interstellar comets leave smaller imprints than we feared. Either outcome advances our knowledge, and that's ultimately what this entire investigation is about. Learning, adapting, and preparing for a future where humanity's presence in space makes understanding these phenomena not just interesting, but essential. Part 15. The Future Frontier. Upcoming missions and what's next. After 3i Atlas. The European Space Agency has already approved a mission called Comet Interceptor, and it represents a paradigm shift in how we study these objects. Unlike traditional comet missions that target known periodic comets years in advance, Comet Interceptor will park itself at a gravitational parking spot called Lagrange Point 2, waiting for a target of opportunity. When astronomers discover a pristine comet making its first passage through the inner solar system, or better yet, an interstellar visitor like 3i Atlas, Comet Interceptor will wake up and race to rendezvous. It will split into 3 separate spacecraft, flying past the target from different angles to capture a true 3-dimensional view. This mission design acknowledges the reality that the most interesting targets are unpredictable. We can't plan a decade-long mission to an object we haven't discovered yet, but we can build a spacecraft, park it in a ready position, and wait. It's the cosmic equivalent of keeping a camera loaded and ready to shoot whatever walks by. Comet Interceptor is scheduled to launch in the late 2020s, and it will wait patiently for something extraordinary to appear. 3i Atlas would have been an ideal target if the timing had worked out, but there will be others. Next-generation observatories will expand our ability to detect interstellar objects much earlier. The upcoming Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will scan the entire visible sky every few nights, creating a movie of the cosmos where anything that moves or changes will be instantly noticeable. Current estimates suggest Rubin will detect dozens of interstellar visitors per year once it's operational, compared to the handful we've found in all of human history so far. This detection rate will transform interstellar objects from rare curiosities into a population we can study statistically, looking for patterns and variations. Understanding heliosphere boundaries more completely requires dedicated missions to the outer solar system. NASA's Interstellar Mapping and Acceleration Probe, known as IMAP, launched recently and is designed to study how the solar wind interacts with the interstellar medium. It will map the boundaries of the heliosphere in unprecedented detail, measuring the flow of neutral atoms that stream in from beyond and the pickup ions created when those atoms get ionized. This data will refine models of heliospheric structure, helping us understand how disturbances propagate and how cosmic rays penetrate. Improvements in cosmic ray detection are happening across multiple platforms. Ground-based arrays like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah are being upgraded with more sensors and better resolution. Balloon-borne experiments continue flying over Antarctica during the austral summer. Satellite missions like the Calorimetric Electron Telescope, known as CALET, aboard the International Space Station measure cosmic rays directly before they interact with Earth's atmosphere. Together, these instruments provide coverage across the entire energy spectrum, from modest cosmic rays that are common to ultra-high energy events that are exceedingly rare. The role of artificial intelligence in space research is growing rapidly. Modern telescopes and satellites generate far more data than human researchers can examine manually. Machine learning algorithms can scan through petabytes of observations, flagging anomalies and finding patterns that would be invisible to traditional analysis. AI helped discover the space hurricane by recognizing the spiral structure in ionospheric data. Similar techniques are being applied to cosmic ray detection, comet tracking, and heliospheric modeling. AI won't replace human scientists, but it will augment our capabilities, allowing us to extract insights from data that would otherwise be overwhelming. New physics often emerges from studying edge cases, and 3i Atlas is the definition of an edge case. It's not quite like solar system comets. It's showing behaviours that challenge standard models. It might be leaving traces in the heliosphere that we haven't seen before. Even if December 19th passes uneventfully, even if the cold spot and cosmic ray spike turn out to be coincidental or misinterpreted, the intensive study of 3i Atlas will have advanced our understanding of interstellar objects, plasma dynamics, and space weather. Every anomaly resolved sharpens our theories. Every mystery explored expands our knowledge. The hopeful narrative here is that humanity is improving its cosmic literacy. We're no longer passive observers wondering what lights appear in the night sky. We're active, investigators sending spacecraft to comets, launching telescopes to map the heliosphere, building detectors to measure cosmic rays, and developing models to predict how all these pieces interact. We're still ignorant about vast swathes of cosmic phenomena, but our ignorance is shrinking year by year as observations accumulate and theories mature. Historical context reminds us how far we've come. A century ago, we didn't know galaxies existed beyond the Milky Way. We didn't know the universe was expanding. We didn't know about cosmic rays, solar wind, or the heliosphere. We'd never sent a spacecraft beyond Earth orbit. The entire edifice of modern astrophysics and space physics has been built in living memory through dedicated observation and theoretical work, and the pace is accelerating. Discoveries that would have taken decades in the past now happen in years or months, because our instruments are better and our international cooperation is stronger. Public participation in science is also growing. Citizen science projects like Galaxy Zoo and Planet Hunters have shown that interested amateurs can contribute to real research, processing data, and finding anomalies that automated algorithms miss. Amateur astronomers discovered several features of 3i Atlas before professional observations confirmed them. The democratization of science, enabled by internet connectivity and accessible data, means that the next major discovery might come from someone's backyard observatory or from a student analyzing publicly available datasets. Invitations to follow future discoveries aren't empty gestures. Anyone interested can subscribe to NASA's news feeds, follow astronomy preprint servers, join amateur astronomy clubs, or simply look up at the night sky with informed wonder. Science is not a closed guild. It's a conversation, and the conversation is open to anyone willing to learn the language. 3i Atlas is one topic in that conversation, but there are thousands of others, each with its own mysteries and dedicated researchers pushing boundaries. The inspirational close is earned because it's true. We stand at a remarkable moment in history. For the first time, humanity has the tools to study the cosmos as an interconnected system. We can track visitors from other star systems. We can measure particles arriving from distant galaxies. We can model the invisible magnetic structures that shape space near Earth. We're still students, still learning, still surprised by what we discover, but we're asking better questions, gathering better data, and building better theories than ever before. The universe still holds mysteries, countless phenomena we haven't imagined, let alone observed. But we're getting better at reading its signs, decoding its messages, and understanding our place within it. December 19th, 2025 will come and go. Earth will cross through whatever region 3i Atlas has created or failed to create. Instruments will record data. Scientists will analyse findings. Papers will be written, debated, revised, and eventually published. And the cosmic conversation will continue, enriched by whatever we learn. Whether the cold spot proves real or illusory, whether the cosmic ray spike signifies a genuine corridor or mere coincidence, we will have advanced our understanding. That's the promise of science. Not certainty, not final answers, but steady progress toward deeper comprehension of the magnificent, mysterious, and dynamic universe we call home. The visitor from another star has given us a gift, the gift of new questions and the opportunity to seek their answers. And that, more than any dramatic revelation or cosmic threat, is what makes 3i Atlas's passage through our solar system truly significant.